Alright, essay questions for Unit 3 exam. First off, describe the action potentials in cardiac, ventricular muscle, and in the SA node. In each phase of the action potentials, describe the channels, ion currents, and membrane potentials involved. In part 2 of this essay, explain the ECG tracing and how each of the P, Q, R, S, and T waves are made. Alright, first, cardiac action potentials are similar to skeletal action potentials in that sodium is used to depolarize the cell, calcium is used to control the contraction strength, and the outflow of potassium is used to establish the resting membrane potential. What sets cardiac muscles apart is the pacemaker cells that automatically depolarize with calcium to start an action potential that has the rest of the heart contract. So one thing that sets cardiac muscle apart is that its resting membrane potential is around -90 millivolts. And this is established by potassium 1 channels. The cardiac contraction cycle starts with phase 0 here. That is depolarization, the depolarization phase, and voltage-gated sodium channels open to depolarize the cell. And at the same time, potassium 1 channels that contribute to RMP are closed. And then phase 1, which is this section here, rapid repolarization then closes the sodium channels from phase 0 and opens potassium and chloride channels to quickly repolarize. Phase 2, which is this plateau, slows the repolarization of the cell by opening voltage-gated calcium channels and potassium channels. The V-gated calcium channels are activated much more slowly than the sodium channels, and the exit of potassium and entry of calcium effectively negate each other in this phase. But the calcium is important because it plays a role in muscle contraction. And so, with calcium flowing into the cell and potassium flowing out at this point, they negate each other, and the cell's polarization membrane potential levels out in this phase. Then phase 3 is the continued repolarization of the cell. So during the plateau phase, more and more potassium channels are opening, and the outflow of potassium drives the membrane potential low enough to then close the voltage-gated calcium channels. And then as RMP is reached, the voltage-gated potassium channels close, and the potassium 1 channels open up to again establish a consistent resting membrane potential down here. Then SA node, cells of the SA node specifically have another chart unique to them. Looks like that. So in the SA node, the process of action potentials is slightly different. The cells in the SA node have unique ion channels that allow them to automatically depolarize and start action potentials on their own. These channels are called funny channels since they are effectively opposite of voltage channels found everywhere else in the body. So the funny channels are voltage-gated sodium channels that open when the cell is polarized and close when the cell is depolarized. Effectively, the opposite of the sodium channels that make this function. And these channels allow the cell to depolarize on its own. Since they're open down here, allowing positive ions in, they slowly depolarize and close up here, so they don't contribute to the curve there. Another thing that sets the SA node cells apart is that once they do hit threshold, voltage-gated calcium channels open to further depolarize the cell. So sodium and then calcium for all of this. And something unique about calcium channels is that they open and close more slowly compared to sodium channels. So compared to the peaks of sodium channel curves, they're sharp here because the channels can open and close very quickly, but calcium channels act slower, so we have a larger peak at the top. Then voltage-gated potassium channels are used to repolarize the cell. And when the cell is repolarized, the funny channels open back up and the SA node begins reaching threshold again. Right, then for ECG, electrocardiogram lines, I'm going to keep this simple. So ECG lines are created from moving currents in the heart, and as an action potential spreads in a certain direction, a charge spreads, and the nodes placed around the heart pick up the fields generated by these charges and print them. And if a charge is traveling towards a node of the same sign, it will be negative, and if a charge is traveling towards node of the opposite sign, then the line will be positive. Positive and negative meaning just whatever's printed. Whatever's printed through the ECG will be above or below this midline. So that determines positive and negative. And so the charges that spread, usually at resting membrane potentials, the inside of the cell is negative and the outside is positive, and then as an action potential spreads, it changes just swaps places, and the charges on the outside of the cell membrane is what is detected by these nodes. And so normally it's all positive, but then as action potential spreads, negative charges start spreading out. So if the nodes are placed like this around the heart, and negative charges start spreading out from the SA and out from the AV, general line points down like this. So negative spreading towards the positive node represents a positive line being created on the ECG. All right, question 2. Describe the events taking place in the left ventricle and aorta during the cardiac cycle. Include the various stages, blood volume changes, pressure changes, opening and closing the valves, and heart sounds. Finally, be sure that you can explain the pressure volume curves for a single cardiac cycle. So the contractions of the heart are organized into systole when the heart is contracting and pushing blood into the aorta, and diastole when the heart is relaxing and filling with blood. So diastole is separated into 3 phases. The first is rapid inflow, when the mitral valve opens to allow blood to flow into and refill the left ventricle. And this blood entering the ventricle is not under pressure from the atrium. So go ahead and mitral valve, semilunar valve, left atria, left ventricle. So in the diastole, blood returning to the atria simply flows into the ventricle, not under pressure at this point. And the second part of diastasis is when the ventricle has reached about 70 to 80% capacity, and passive flow of blood into the ventricle is slowing as it fills near the top. And the third phase is when the atrium contracts to fill the remaining 20 to 30% of the ventricle. So ventricle is now filled, systole begins, and it is also organized into 2 different phases. The first is isovolumic contraction. So contraction of the ventricle begins, pressure builds in the ventricle, and once the ventricular pressure exceeds the atrial pressure, the valve connecting them closes and is responsible for the first sound of the heart, the lub sound. And so at this point, the ventricular pressure has exceeded atrial, but has not exceeded the aortic pressure quite yet. So both of these are closed at the moment. So there is no change in the blood volume as pressure continues to rise during this contraction. And the second phase of systole is ejection. So once the ventricular pressure reaches or exceeds about 80 millimeters of mercury, the semilunar valve opens to allow blood to exit the ventricle and enter the aorta. And pressure usually peaks around 120 millimeters of mercury. And once contraction is ended, pressure begins to go back down. And once ventricular pressure goes below aortic, this valve is once again closed. And the closing of that valve is what's responsible for the second sound of the heart, the dub sound. And once ventricular pressure goes below atrial, mitral valve opens back up, and the cycle continues with blood flowing back into the ventricle. And all of this charted out looks something like this, with the ventricle filling with blood passively. Usually there's a little pump there as the atria contracts to give it that last little push of blood to fill the ventricle all the way. Then systole begins contracting. This is the isovolumic, since volume is not changing, pressure is increasing, so that would be the 80 mark when the pressure of the ventricle can push blood into the aorta. Rises to about 120, goes back down, back in diastole now, heart is relaxing, pressure's going down, volume isn't changing because it has not reached the atrial pressure yet, but once it goes below that, it starts filling back up. Now on to question 3. Describe the mechanisms for inotropic and chronotropic actions of norepinephrine and acetylcholine on the heart. Explain the role of calcium in cardiac muscle contraction, and include the mechanism of its release into the cytosol and its return to the SR and extracellular fluid. So, inotropic regulation is the method the body uses to regulate the contractile strength of the heart, and chronotropic mechanisms control the heart rate. So acetylcholine is used by the parasympathetic nervous system to slow the heart and maintain its resting heart rate, while norepinephrine is used by the sympathetic nervous system and the endocrine system to upregulate the heart to make it contract harder and faster. So the method that acetylcholine uses to regulate the heart rate is through G proteins, which are activated by the acetylcholine. And once activated, its released subunits will activate potassium channels to open and lower the membrane's RMP, as well as decrease CAMP, which will increase the threshold of the cell and flatten the slope of the cardiac cycle. So, two things we've got here. So what it does is the extra release of potassium drives this RMP down, CAMP increases this threshold, as well as flattens this, which means is specifically this line here that connects base to the point at which systole ends. And so flattening that curve looks like this. So shallower angle, and this represents the volume held within the ventricle as the heart is beating. And so shallower angle like this, lower range of volume. So total cardiac output is lessened. And when we're resting, that's fine. And then norepinephrine, on the other hand, is utilized by the sympathetic nervous system and endocrine system to increase the heart's output. So norepinephrine binds to beta-1 receptors on the cardiac cells and works to increase CAMP, cyclic AMP, within the cell, increasing calcium, which has a handful of effects like increasing the steepness of the cardiac slope, so driving it up here instead, increasing the total volume that the heart outputs, also makes threshold more negative to increase the heart rate and increases contractility. So instead of pushing RMP and threshold away from each other, norepinephrine's effect is that it brings it lower. I suppose that's more important for the SA cells that control action potential. So if this is brought lower, it causes action potentials to happen much sooner. And so cardiac muscle is also unique from skeletal muscle in that it cannot change its contraction strength by recruiting more muscle fibers. They're all being used every time the heart beats, so its strength is determined entirely by the amount of calcium released within the cell. And that changes the strength and length of time for contraction. So when a cell's membrane reaches threshold, V-gated calcium channels are opened to allow extracellular calcium into the cell, and this calcium binds to receptors on the sarcoplasmic reticulum to release calcium stored within the cell. So it's calcium-activated calcium release. And so the amount of calcium allowed into the cell controls the amount of calcium released from the SR within the cell. More calcium means stronger contraction. And once contraction needs to end, sarcopumps are used to put calcium back within the SR, and the additional calcium that was brought in from outside the cell, a new sodium calcium pump unique to the heart, works to remove the extra calcium. All right, question 4. Explain the mechanism by which fluids normally move out of and into capillaries. Describe the various forces involved and how these forces differ at the atrial and venous sides of the capillaries. Then, using inflammation as an example, describe the mechanisms responsible for edema. In part 2 of this essay, describe the baroreceptor reflex, include all of the components of the reflex, and describe the chain of events that would occur if systemic blood pressure suddenly dropped. Explain how each of the following is involved in the regulation of blood flow: myogenic autoregulation, paracrines, and sympathetic regulation. So for the fluid flow through capillaries, hydrostatic pressure, osmotic pressure, blood colloid, osmotic pressure, interstitial colloid, osmotic pressure, and others all play a role in applying a pressure to move fluids into or out of a capillary. So first, we'll work with blood pressure. So as blood leaves the heart, it's under systolic pressure, and that quickly fades to diastolic pressure between heartbeats, jumping between 120 and 80. And as blood makes its way through the body, this oscillation becomes much less and stabilizes, and by the time blood is reaching a capillary, it's usually around 30 millimeters of mercury in pressure. And once inside of a capillary, the space is very tight. Usually capillaries only allow one red blood cell. That's about the scale within a capillary at a time. And this puts friction on red blood cells moving through, and by the time blood is entering a vein after passing through a capillary, the blood pressure has dropped to about 10 millimeters of mercury as it's leaving. Alright, then BCOP is an osmotic pressure that moves water towards areas with more solutes, and that area in this case is the inside of the capillary. So BCOP, this specific pressure, pushes fluids inside the capillary, mostly because of contents of the blood, albumin, which is a very, very abundant protein within blood that is too large to move through capillary walls. So this high concentration of albumin makes up most of the reason for BCOP. And the pressure provided by BCOP is around 28 millimeters of mercury. And then there's also an ICOP that is based on solute concentration that moves water out of the capillaries into the interstitial space. And that usually represents 8 millimeters of mercury. And finally, there is interstitial fluid pressure, and this comes from the effectively suction pressure provided by the lymphatic system, taking up interstitial fluid to be returned to the heart. It's just supposed to be a valve. The reason this provides a suction is because once stuff enters, it can't go back out. So it only takes fluids away. And this adds about 3 millimeters of mercury worth of pressure. And so we add all of this up with 30 here, 8 from here, 3 from here, turns to 41. Out and 28 in, for a total of 13 net millimeters of mercury worth of pressure pushing fluids out of the capillaries on the arterial side. But once we're on the venous side, blood pressure drops significantly, but everything else stays the same. These are all solute-based pressures, and this remains the same since it's based entirely on interstitial fluid. And so solutes that usually control these pressures remains the same. Albumin can't exit or enter, and interstitial fluid remains relatively the same. So we still have ICOP representing 8 out. BCOP is still 28 in, and we still have 3 provided by the lymphatic system. And so instead of 30, we have 10, reducing this number by 20. Then we have a net 7 millimeters of mercury being pushed back into the capillary on the venous side. And then edema is the irregular collection of fluids in the interstitial space. And inflammation from our immune system can cause edema with hormones by changing the permeability of solutes across the capillaries. And then the baroreceptor reflex will detect changes in blood pressure and help the body keep blood pressure stable. So with the baroreceptor reflex, it has cells located at these points in the aortic arch and carotid sinuses. And as these are stretch receptors, and so as they're stretched by maybe an increase in blood pressure, so their action potential rate is determined on how much they are stretched. So high blood pressure stretches arteries more, and as these cells are stretched more, they create more action potentials. And if blood pressure goes down, they are not stretched as much, so they do not create as many action potentials. And all of those action potentials are conveyed to the brain, and the brain can use them to respond to increase or decrease cardiac output, depending if the baroreceptors are sending a lower frequency or higher frequency of action potentials. And so in the case when the blood pressure drops, the baroreceptors would not create as many action potentials. The brain would recognize this as a decrease in blood pressure, and in response it would increase the sympathetic activity to the heart to have the heart beat faster and contract harder, restoring normal blood pressure. So the sympathetic activity would increase norepinephrine, decreasing this threshold, increasing this cardiac output. Then myogenic regulation is due to smooth muscles' ability to recognize stretch on their own and contract. In response, and this ability comes from mechanically gated calcium channels. This helps reduce increased blood pressure by restricting arteries. And for greater control of blood pressure, the paracrine system is used, and this involves endothelial cells releasing signaling molecules to alter vasoconstriction. And paracrine regulation and increased metabolic activity in an area will simulate vasodilation and increase blood flow in that area. And increased blood flow due to these stimuli is called reactive hyperemia. And finally, question 5. Describe the composition of the blood. Include the components of the plasma. Describe the mechanism by which red blood cells are removed from circulation. Especially explain how heme is broken down and what happens to the various components of the heme. In part 2 of this essay, describe the 3 mechanisms that contribute to hemostasis. Special attention should be given to the role of the platelets and coagulation cascade. For the coagulation process, describe the intrinsic, extrinsic, and common pathways. Also discuss the role of TPA, plasminogen, and plasmin. Alright. So the normal composition of blood is made up of 55% plasma and 45% formed element, which is red blood cells, white blood cells, platelets. And plasma itself is 92% water and holds colloidal proteins. These proteins contribute to the osmotic pressure maintained within the blood, making sure that too much fluid isn't lost. And then in the formed element, red blood cells make up the majority of its volume. Since red blood cells lack nuclei, they only last for around 120 days. And macrophages throughout the body, specifically, they're concentrated within the spleen that does a lot of the work to clear out old red blood cells. They catch damaged or dying red blood cells and break them down to recycle certain components. The heme in red blood cells is separated from its iron atom and turned into biliverdin. The iron specifically will be reused by being packaged and resent to red bone marrow, but the biliverdin at this point cannot be reused. It'll be converted into bilirubin and attached to the albumin in the plasma, and it will be transported to the liver, where it will be altered by having glucuronic acid added to it. So in the blood, it is unconjugated bilirubin, and once changed in the liver, it is conjugated bilirubin once it's had the acid added to it. And the glucuronic acid added to it makes the bilirubin more polar. And conjugated bilirubin becomes a component of bile and is excreted into the digestive tract. So, unconjugated bilirubin attached to albumin in order to transport it, since it's not polar at this point, it needs albumin to flow through the blood. Reaches the liver, becomes conjugated with glucuronic acid, excreted into the stomach. Once there, the acid here breaks off that glucuronic acid. And once it is removed, it is known as urobilinogen. So once there, it can be re-extracted from the intestines. So it can re-enter blood and be reused in the liver to become a component of bile once again. Or it will end up in the kidney, where it is turned into urobilin, and excreted in urine. If urobilinogen stays in the digestive tract, it'll turn into sterocoubilin and be excreted in the feces. Then hemostasis is the ability of the body to stop bleeding. First method available to the body is vascular spasm, and in this process, pain can stimulate smooth muscles around an affected area to contract, and this will lessen or even stop blood flow through a damaged vessel. This, though, is only a temporary measure, because the smooth muscle will need to eventually relax and the bleeding will continue. So, the next more permanent method is platelet aggregation. This is caused by von Willebrand factor binding to collagen fibers that are exposed when a vessel is damaged. So, vessel is damaged, allowing blood out. Collagen fibers kept within the vessel wall here, but once exposed, von Willebrand can interact with them. Yeah, von Willebrand factor attaches to the collagen fibers, and platelets, when they come in contact with them, they can bind to the von Willebrand, which then connects them to the collagen, and this activates the platelets. And once activated, the platelets form strong bonds to the collagen, grow larger, and present fibrinogen on its surface. So it sends out, grows larger and larger to fill the gap. And if another platelet comes in contact with a bound platelet with fibrinogen, it will also be activated, attach, and grow to fill the hole in the vessel. So more and more platelets are activated by other platelets once they've bound to von Willebrand and collagen. Finally, there is coagulation, which forms blood clots. And the proteins that are responsible for this process are always in the bloodstream in a deactivated state until they are activated. And once activated, they create a cascade of recruitment to bring many molecules together to fix the vessel. And for this cascade to begin, there is an intrinsic path that is activated by the exposed collagen of the vessel, and the extrinsic pathway, which starts the cascade outside of the vessels when destroyed tissue releases tissue thromboplastin. So both pathways converge to a common cascade after a few steps. So with intrinsic, collagen starts so these factors in the blood clot pathway are numbered and named after the order that they were discovered, not necessarily the order in which they play a role. So this collagen starts by activating factor 12, which activates factor 11, which activates 9, which activates 10, and the extrinsic pathway, which starts with signals outside of the blood vessels, activate factor 7. So signaling molecules outside the vessels activate 7, which activates 10. So So at this point, the paths have converged, and from 10 on, we have a common pathway. And the purpose of all of these, this activates this activates this, is that basically as we go down these steps, it effectively multiplies the number of molecules being activated each time, as 1 factor 12 activates a few 11s, and if every one of those 11s activates a few 9s, then it's all just multiplying itself to recruit a bunch of molecules in order to fix these problems. And so, once we get to the common pathway, factor 10 activates prothrombin. And turns it into thrombin, which then goes on to activate fibrinogen into fibrin. And fibrin is specifically what creates the clot. Then blood clots cannot stick around forever. It's got to heal up eventually, so the body has created a system where the creation of fibrin also activates a chain reaction that will eventually degrade the clot. Once fibrin is created in large amounts for a clot, it will activate endothelial cells within the walls of the blood vessel to release tissue plasminogen activator, which converts plasminogen found within the blood into plasmin, which will then work to break down blood clots.